complex numbers, and there is a fallacy around that the reason complex numbers were created was to solve quadratic equations. That's actually false. That's not why the imaginary numbers came up. However, it is very useful for solving quadratics. Because, of course, we get this simple quadratic here, x squared plus 1 equals 0. Before now, we go, oh, there's no solutions. More technically correct, of course, to say no real solutions, because there are actually solutions. We define a new number, and that new number is actually a letter. And that letter is... Okay, now let me correct the first incorrect thing you've done. No, it's not I. It's the Greek letter iota. Okay? The symbol that's used is the Greek letter iota. So, iota, more conveniently though, we do call it I. But that's not what it is, it's iota. It is the square root of -1. Or maybe it's more correct to say the definition is not that it's equal to the square root of -1. It's probably more correct to say I squared is -1. Our imaginary number. It is an unfortunate choice for a name, imaginary number, because it implies it doesn't exist. But it does exist. They just called it imaginary. Same as negative, they just decided to use the word negative. It's just another type of number. So people again have this misconception that they don't exist, but they do exist. All numbers exist. All mathematics exists. So now we can carry on with this equation. X squared equals -1. So we get x equals plus or minus the square root of -1. So x is plus or minus I. But what I was saying was that was not the original problem that brought around. The actual original problem was how do you solve a cubic equation? And in order to solve a cubic equation, you know how like we have our, for quadratics we have x equals -b plus or minus, etc. Very simple formula. There is a general formula for cubics, much more complicated, but in order to use it, you need to find the square root of negative numbers. And that's where this all came from. It was actually solving cubic equations, not quadratic equations. Now, what we basically do with complex numbers is we can break them up into two parts. And we usually write it as x plus iy. By the way, they don't always use I or iota. Sometimes they use j. You sometimes see j used. It's just basically defining the two different parts of a number. You actually have been dealing with complex numbers all your life. Just exactly right. No, I was not 0. That's always the square root of -1. So we define a few things here. All complex numbers have a real part and an imaginary part. Let's say all the numbers you're dealing with, the imaginary part was 0. So the real part of a complex number is x, the imaginary part is y. No, it's just y. It's not iy, it's y. The imaginary part is y. So if we have 3 plus 5i, the real part is 3. As I say, the imaginary part is 5, it's not 5i. If the real part is equal to 0, then that's a pure imaginary number. There is no real part. Hey, here's some examples of pure imaginary numbers. Square root of 3 times I. -6 times I. Any multiple of I. Just has no real part. And what you're used to, real numbers, that's when the imaginary part is equal to 0. Here are some examples of real numbers. 3/4. Pi. E. -4. Every complex number has a conjugate. Now, if you think about it, complex numbers are surds, because the imaginary part is the square root of -1. And so if you're writing it as x plus some multiple of the square root of -1, you're talking about a surd. So it satisfies all the surd laws. And just like you have a conjugate surd, you can have a complex conjugate number. So the conjugate, you change the sign on the imaginary part. X minus iy, symbolised often with just a bar over the top of z. So if z is -2 minus root 7i, its conjugate is -2 plus root 7i. Now, unlike when we're playing with normal surds, it doesn't matter which one you make plus or minus. A conjugate has to be the imaginary part. Okay, so imagine these are all the numbers we know. The world of numbers, complex numbers, which can be written as x plus iy. And up until now, we've only really been dealing with a fraction of that set of numbers. We were dealing with all the ones where y was equal to 0. And so what we now know is, hey, there's this other set of numbers over here, imaginary numbers. And notice they don't overlap. And this is where y does not equal 0. Okay, back over the real numbers. Started dealing with, well, rational numbers. And we didn't know what surds were and things like that originally. And then we discovered irrational numbers, pi being the most famous, of course. Inside the rationals, after a while, because when we were, I don't know, first grade, whenever we start counting, we're just dealing with whole numbers. But then we learn about fractions. And by fractions, I'm talking about fractions where top and bottom are integers, so they're rational. And then we said, hey, there are integers. And inside the integers, we have the natural numbers. And then we have this really weird thing, 0 sits by itself. But we do place it inside the real numbers. Because whilst there's debate about whether it exists, it certainly is real.
Are natural numbers just the counting?
Natural numbers are the counting numbers, yeah. And then overlapping all these are negatives. You can have negative fractions and negative integers. Can't have negative natural numbers. And you can have negative irrational numbers. So back over here in the imaginary numbers, what can we do with these? That's about it, really. We break them up into imaginary numbers and pure imaginary numbers. The imaginary numbers cannot be ordered, so you cannot say one imaginary number is bigger than another imaginary number. And that's the difference. Because when we start talking about order, we have to be able to place it on the number line. So we know, oh, that one's further away from 0. This one's closer to 0. But when you start talking about imaginary, they don't sit on the number line. So how do you order them if they don't sit nicely on our number line? Basic operations. So as I said, they are basically surds, so the operations are the same as surds. So we add them, and, well, not only could you think of it like surds, you can think of it like algebra. You add and subtract like terms. So we get -4 minus I. Same with subtraction. See, 12 minus 5i. Who thought when you started doing algebra you were actually playing with imaginary numbers sometimes, if the pronumeral was I? Multiplication. Well, it's like a binomial product. First outside, inside, last. But there is a difference, of course. Whenever we see I squared, that's actually -1, so we can tidy up. -6i squared is actually +6. After a while, you probably neglect writing I squared and write straight +6. I mean, hopefully it will become a natural thing. And so we get -26 plus 32i. Now, division is what we call realising the denominator. In surgery, it was called rationalising the denominator because you wanted a rational number in the denominator. Well, with an imaginary number, you want a real number in the denominator, so we call it realising. We're going to multiply by the conjugate. And when we do that, on the bottom now, we have the difference of 2 squares. But when I'm dealing with imaginary numbers, the difference of 2 squares becomes the sum of 2 squares because of the I squared. So 64 plus 4 is on the bottom of this one, and it tidies up. The purpose of realising the denominator, exactly the same as the purpose of rationalising the denominator, is so you can compare. You can compare numbers. You can't compare fractions unless the denominators are the same. And that's why you need to make the denominators the same in fractions before you add or subtract. How can I add and subtract these things if I haven't got the same denominator? And so that's the whole reason why we rationalise and realise denominators, for the sake of comparison. Hey, some basics when we're playing with conjugates. If you want to find the conjugate of a number, it doesn't matter the order you do it in. You could add the 2 numbers first, then find the conjugate, or you could find the conjugate of each individual bit and then add them. The order doesn't matter. Same with multiplication. Same with division. This one's useful. You multiply a number by its conjugate. Z, well, basically that's what we just did, realising the denominator. So you get the sum of 2 squares, the real part squared plus the imaginary part squared. And if you want to find the reciprocal of a complex number, then all I've done is I've multiplied top and bottom by Z conjugate. Because basically what we're saying is, oh well, the reciprocal will be the conjugate over x squared plus y squared, which later we'll have another term for, and it'll be easier to say, but we haven't learnt that term yet. We'll get there. Right, want to find the reciprocal. So then it's just 4 plus 3i, conjugate, sum of 2 squares, 16 plus 9. there's the reciprocal of that complex number. Okay, complex equations does not mean hard equations. It just means equations involving complex numbers. Okay? But it's like when we dealt with quadratic identities, and even surdic equalities. The real part must equal the real part, and the imaginary part can equal the imaginary part, because remember the two sets, there's no overlap. So it's like having two equations in one for the reals, one for the imaginaries. So if you have A1 plus B1i is A2 plus B2i, then there is no choice. A1 must equal A2 and B2 must equal B2. The real part equals the real part. The imaginary part equals the imaginary part. So if I want to solve this sort of equation, well, there's several things I could do. I could expand out first, or I could divide. Which way did I go? I expanded out. Okay. So let's group the real parts together. The real part's 2x minus 3y, so that must equal 4. The real part must equal the real part. 3x plus 2y, that must equal the imaginary part, negative 2. A couple of simultaneous equations to solve. And then we can find, well, there you go, x is 2/3 and y is 16 on 13. Simultaneous equations, still no different. You want to solve a simultaneous equation, you want to make a coefficient of the pronumeral the same. I'll do exactly the same thing here. It doesn't matter that the coefficient happens to be an imaginary number. Still the same idea. It's still mathematics. So I'm going to get rid of the w's. So I'm going to make the coefficient of both w's 2i, which means multiplying the bottom one by 2. So the w will eliminate. And I end up with 3z is 2 plus 5i. So I know what z is, 2/3 plus 5/3 i. I can substitute back in and work out w. And so 2iw, 10/3 plus 4/3, divide by 2i. We don't leave complex numbers with I in the denominator. Unlike surds, where it's perfectly acceptable to leave a surd in the denominator, 1 on root 2 is fine. We never do it with complex numbers. So we always want to break it up into, oh, this is the real part, this is the imaginary part. So 2/3 minus 5/3 I, once we've realised that denominator. So there's my answer to the simultaneous complex equations. Okay, well, there's a little start. So Cambridge, and then Patel, there's a handful of questions. In fact, just 2 questions.